Stand anywhere on a circle's edge and look at the same arc. The angle it makes will be exactly the same, no matter where you're standing. That's one of the most surprising facts in this entire chapter, and it unlocks everything about cyclic quadrilaterals, too. Here's the core theorem. The angle an arc subtends at the center is always exactly double the angle it subtends at any point on the circle outside that arc. So if an arc creates a 40-degree angle at the center, it creates exactly 20 degrees at any point on the circle's edge, no matter which point you pick. Because the proof only ever uses isosceles triangles formed by radii, which are the same length no matter where the point sits. This gives a beautiful direct consequence. Angles subtended by the same arc at different points on the circle are always equal to each other, since they're all just half of that one fixed central angle. And here's the most famous special case. A diameter subtends a straight angle 180 degrees at the center, so at any point on the circle, it must subtend exactly half of that, 90 degrees. This is why the angle in a semicircle is always a right angle. Now flip the idea around. If a segment AB creates equal angles at two other points, C and D, on the same side of AB, then A, B, C, and D must all lie on one single circle. They're concyclic. Why? A, B, C already determine a unique circle. If D sat off that circle, the angle it makes would have to be strictly bigger or smaller than C's angle, which contradicts them being equal. So D has no choice but to sit exactly on that same circle. When all four vertices of a quadrilateral sit on one circle, it's called a cyclic quadrilateral. And it has a signature property. Its opposite angles always add up to 180 degrees. Here's why. Each angle is half of the central angle for its opposite arc, and the two opposite arcs together sweep the full 360 degrees around the center. Half of 360 is 180, so the two opposite angles must sum to exactly that. And the reverse holds too. If a quadrilateral's opposite angles add to 180, it's guaranteed to be cyclic. Try this. A cyclic quadrilateral PQRS has angle P, x 2x plus 10 degrees, and angle R, x 3x 20 degrees, and P and R are opposite angles. Since opposite angles in a cyclic quadrilateral always sum to 180, we get 2x plus 10 plus 3x 20 half 180. That simplifies to 5x, 10 over 180, so 5x for 190, giving x for 38. Substitute back angle P for 238, 110 for 86 degrees, and angle R for 338, 20 for 94 degrees, and sure enough, 86 plus 94 for 180, confirming the answer. Quick check. The question's on screen. Pause if you like, but try it first. 10 seconds, go. In a cyclic quadrilateral, opposite angles sum to 180. If one angle is 75 degrees, its opposite is 180 minus 75, which is 105 degrees. The answer is 105 degrees. The angle at the center is always double the angle at the circle's edge. Angles in the same arc segment are always equal. A diameter always creates a 90-degree angle, and a cyclic quadrilateral's opposite angles always sum to 180. Free notes in the description. Next chapter, we measure perimeter and area. Subscribe to Clarix.